Alright, welcome back. We are looking at this example again. And just to recap, this example was the example with beetle population, and we used the logistic growth model to approximate the generations, y sub 1, y sub 2, y sub 3. And we estimated it with successive iterations, which essentially was based off of previous values. Like to get y sub 1, we use the initial population plus the rate at that point of population growth. And then similarly with the other generations, y sub 2 generation, we used the previous y sub 1 plus the rate at 1 y sub 1 or y of 1, and similarly with y sub 3. So the reason why we did it this way was, well, for one, it's not a terrible way to do it. It's kind of straightforward calculation, and the other reason is because that's how the My Open Math program did a similar example. But I did want to show, because we are and have been doing separation of variables and integrating factor examples, the way we could use that here. So the way we use that is separation of variables here and using partial fractions, which is a fun topic in itself. So if you remember our differential equation that we wrote, then we would like to write this as a fraction. So factor out of 1/160th from the parentheses, and we get dy dn being equal to y over 160 times 160 minus y, and then, so we wrote it as a fraction, and then we can separate the variables. As I mentioned, that's how the method we're gonna essentially use. So separating the variables, if you get the y's on one side and the dn on the other, that's really all we can do. We're gonna end up with 160 over y times 160 minus y dy on the left side, and then that's equal to dn on the right side. So we have separated the variables right over here, and this is where we realize on this side we have a fraction, and if we tried to integrate now it'd be a problem because we don't really have a good way to do that just by itself other than partial fractions. So that's what we're going to do. So partial fractions, I kind of already set up a template here to make life easier for myself. And when we do partial fractions, we know that if you have a fraction over, and its denominators written as its factors, you can split that up as one fraction over one of its factors plus another fraction with a constant on top over its other factor. And that our goal is to essentially find what those constants are. To start that, we multiply both sides by the LCD, which is just y times 160 minus y, distributing that to each of the terms inside the parentheses. We just get 160 on the left side, which is nice. being equal to, when we distribute the LCD to the a over y, the y cancels out, and we are left with a times 160 minus y, plus when we distribute it to the b over 160 minus y, the 160 minus y cancel out, and we are left with by. So what's nice about this is we can manipulate the left side and right side to essentially match coefficients where because they're going to be equal if you rearrange things. So let's rearrange things to show you what I mean. On the left side, we can actually write this as a linear expression of 0 times y plus 160. And then on the right side, after distributing, and I'm going to just kind of skip that step just due to kind of time. When you distribute and rearrange things to get like the y's on the left side, you can write it as negative a plus b times y, and then plus 160a. And what's nice about that is now we have something y, 0y, plus some constant, 160, equal to something y, which is negative a plus b times y, plus some constant, 160 times a. And what's awesome about that is, well, if the left side equals the right side, negative a plus b, the coefficient of the right side, times y, has to be equal to 0, which is the coefficient of something times y on the left side. And the other thing that has to be true is the constant has to be equal. So on the right side, 160a has to be equal to the constant on the left side, 160, and that makes this relatively straightforward to solve because we just divide both sides by 160 to get a equals 1. And in this case, we also know that b will equal a, so b equals 1. So voila, we know our partial fraction breakup is just going to be 1 over y plus 1 over 160 minus y. So let's go back to that, which I have already written here. This problem can be a lot. This can make it a long video or a shorter video, which ideally want to make it a slightly shorter video. So, knowing that our fraction splits up to 1 over y plus 1 over 160 minus y dy being equal to dn, now we can integrate both sides to get the natural log of the absolute value of y minus the natural log of the absolute value of 160 minus y being equal to n plus, and I'm going to write c sub 0 as just some constant. And to do more on that, using log properties, we can just essentially write this as 1 log absolute value of y over 160 minus y being equal to n plus c sub 0. And then the reason for doing this, or what makes this nice, is if we place e and use that as the exponent, using properties of logs again, they act as some kind of cancel out thing, and we end up with the absolute value of y over 160 minus y being equal to e to the n plus c sub 0, which we can simplify. And notice this is just addition. This the exponent on this side here is just addition of exponents, and we can actually write that as e to the c sub 0 times e to the n, which I'm going to do. And then also on top of that, absolute value essentially means plus or minus. So rewrite, getting rid of the absolute value, we can just write y over 160 minus y being equal to plus or minus e to the c sub 0 times e to the n. Right? And really just rewriting that as y over 160 minus y being equal to, so this is the reason why I put c sub 0 in the first place. This plus or minus e to the c sub 0 is just a number, so it's just a constant. So we can really just say it's some constant c, right? We don't need to keep writing that, it makes it look weird. And then we still have e to the n. And I mean, that essentially is our implicit general solution, but we also do have an initial value here, and our initial value is y of 0 being equal to 55 beetles, right? So plugging that stuff in, we know we have to get what c is. I'm going to move this up a little bit. Y of 0 being equal to 55, we know we can write 55 over 160 minus 55 being equal to c times e to the 0, which essentially just means c is equal to 55 over 105, which does just equal 11/21. So what is nice about that now is our differential, or not our differential equation, but our equation can just be written in terms of y being equal to, y over 160 minus y being equal to 11/21, or 11/21 times e to the n. And I'm only boxing this because we still have more to do. And you can see I actually already solved it. But to get y by itself, because that's essentially what we want, we can essentially multiply both sides by 160 minus y to get y on the left side being equal to 11/21 times e to the n times 160 minus y. And kind of simplifying a little bit, we can multiply everything by 21 to get rid of the fraction. Oops, I'm going to multiply it there, and then there, and then what that gives us is a slightly simpler equation to deal with, making it easier to solve for y, and distributing this in there, we get 21y being equal to 1760 e to the n minus 11 e to the ny. And then when you move the y term to the left side, you can factor, and I'm just telling you that step because I'm running out of space. But it's not a bad step to write if you have the space. So I am just going to actually write, when you factor the y out, you get y times 21 minus 11 e to the ny. I factored out the y. Y times 21 plus 11 e to the ny being equal to 1760 e to the n. And then we divide both sides by the 21 plus 11 e to the n. You get this equation where y is by itself. And then finally, because you probably already forgot what we were doing, because I did, we are looking at beetles, right? Beetles, their population, each generation as n equals 1, 2, and 3. So again, we have solved we got the exact result of what the population would be. So when you plug in our values, which now I'm just going to state them because again this has been a long example when you do it this way, but that's part of the fun of doing differential equations. If you have the first generation where n equals 1, you end up with 93.9896. Second generation, 127. Beetles, by the way, and third, 143. And note, when you look at the results, the first and second way are different, right? Slightly different. And of course, as you get farther, you could see that it seems to be even get off even more. And I would say that should probably make sense because the first way we did it in the first place was really just an approximation, right? So, and we were using the previous values and the rate of the previous value to get the next value. So you're going to be off by a little bit. Whereas using the partial fractions with separations of variables, we're getting the exact answers. So I will leave it up to you to decide which way you think would be the better way. And that was it for this video.